what Birch reduction does is it combines elemental sodium with an amine and alcohol to turn a benzene into what we call an isolated diene. So specifically, if this were to happen with an unsubstituted benzene like we have here, our product would be an isolated cyclohexadiene, two double bonds that are far apart from each other in a 1,4 position on a cyclohexane. Okay? Now, if you take a closer look at these reagents, they might look familiar because these are very similar to the reagents that we use on a dissolving metal reduction. This is a reaction from Orgo 1 that we learned a long time ago that worked with alkynes, and it was a radical-mediated mechanism. Well, it turns out that this mechanism is really the same exact mechanism, except it's going to work with benzene instead of with an alkyne. So let's get right into it. The mechanism for this reduction is going to proceed through elemental sodium, which means it's going to possess just one electron, okay? When that one electron donates to any of the carbons, we're going to have to break a bond, okay? But this is going to be a mechanism where we have a combination of half-headed arrows and normal arrows, just like the dissolving metal reduction, how there were some arrows that moved one radical and some arrows that moved a lone pair. So when we make that bond, we have to break this bond in order to make room for the radical. And in order to keep these charges as far away from each other as possible, or these intermediates as far away from each other as possible, this double bond is going to ionize into a lone pair onto the very bottom. So basically, the furthest position possible from the radical, we're going to get an anion. So let's go ahead and draw the product of this first step. What we're now going to get is a single radical at the top, double bonds on both sides, and now a lone pair at the bottom, which is going to be a carbanion, okay? So this intermediate is called a radical anion, which makes sense because that's what it is. It's a radical and it's an anion. Now, guys, this is where our ethanol comes in. Our ethanol is going to serve as a protonating agent, okay? Now, just so you know, ethanol isn't the only alcohol you can use. Some texts will use butanol. Doesn't matter, guys. It's a source of hydrogen. That's the biggest deal. So, ATOH, my anion is going to grab the H and give a negative charge to the O. So now what I'm going to get is a molecule that looks like this. I've got my two double bonds. I still have my radical, but now I have two H's at the bottom because I had one originally, and now I just added a second one, which is the one that came from the ethanol. Okay? At this point, I react with another equivalent of my elemental sodium. That elemental sodium is going to donate an electron to that same location, and now I'm going to get a lone pair anion. Okay? So this is just a carbanion. Intermediate. Okay? And guys, this reaction just repeats itself. That's one thing about maybe dissolving metal reduction. If you recall, it was the same thing twice. So here, we would react again with another equivalent of ethanol. And we would wind up getting our isolated diene, because now I've got H's, two H's on the bottom, I've got two H's on the top, and that's the ugliest H ever, sorry. And I've got my isolated diene, which is this molecule here. And so that's really it. That's the mechanism for Birch reduction. And now